Welcome everyone to this CI Compass webinar. I'm very excited to introduce Ryan Berkheimer from NOAA. He's a physical scientist at the National Centers for Environmental Information, and this is part of the NOAA's National Satellite Data and Information Service. His role there is the architect of the Open Information Stewardship Service. He's also involved in the Digital Twin Earth Framework specification, and he's a member of multiple cross-agency working groups. So I'm excited to have Ryan present on the NCEI's work with knowledge graphs, and not only with the technical work, but also the vision that drives this implementation effort. So I guess I forgot to say the title of the webinar. It says Enabling an Iterative Open Science Transformation to the Geoverse at NOAA with a Federated Knowledge Mesh. So with that done, I will leave it to you, Ryan.
Great. Thanks, Don, for that nice introduction. Let's put the presentation up here. Move my controls. All right. So, as Don said, I'm Ryan, and this is a slightly modified version of a talk I gave at AMS this year. At AMS, I had a lot more co-authors here, just representing NCEI, NESDIS, and NOAA. On this, I'm a physical scientist, and my role is as the archive architect. Let's go to the next page. And jump right in. So where are we going? You see this word up here, Geoverse. So this Geoverse concept, was defined by the UN GGIM, Geospatial Expert Committee. And they outlined a position paper essentially that, described in concept this sort of state of where we are and state of where things are going, to try to tie everything together, and especially with that geospatial view. Traditionally at large enterprises like NOAA, NASA, USGS, we've achieved this sort of state where we have a lot of these spatial data infrastructures. And what the Geoverse paper kind of says is, let's start collectively moving, this is actually already happening, but we should take some ownership of this, through this system of systems step change where, it's not like my system is a system of systems. I mean, that's true, but it's more like this distributed, state of things is really this global system of systems. And we have machines and humans and everything. And we'll use this step change, sort of system step change, so an iterative approach, to get ultimately to this Geoverse. And this is kind of like the ideal reality that we see as sort of 5-10 years down the road. Like what is the horizon look like? And this is Web 3.0, right? And that's Web 3.0 in the RDF space definition, right? The semantic web definition, more than like the cryptocurrency definition of Web3. So very specifically talking about Web 3.0, although it does include, some capabilities include sort of that sort of blockchain technology. And to affect this change, we rely on this very old construct of the DIKW pyramid, where you have data, information that contextualizes data, provides some context, knowledge which captures and holds that data, and here I got things a little, this is a device, but here we're putting it in information in context to answer questions, and then wisdom ultimately is enabled by this. And this is really exciting, I think, framing, because it's easy to understand and easy to parse, and it kind of sums like the entire purpose of what's going on, and what we're trying to do here. It really captures that, and in an easy to understand way, and sort of a simplified way. And so this Geoverse idea goes on to define all these different pathways You know, how do we get from SDIs or, you know, pre-SDI land, which some developing, you know, countries and infrastructures are at, you know, through SDIs to system of systems. And they provide this set of tables. So they call these pathways, you know, they're divided into swim lanes. And they go, you know, they're categorized in terms of, you know, strategic pathways like standards, technology, and there's 12 of these, I think I'm getting that right. And they go, you know, what does it look like in SDI land? And then what do we anticipate it looks like in this future geospatial information ecosystem? So, you know, you can see here, you know, in this swim lane, community of practice. Right now, we've kind of achieved sharing and leveraging data and technology standards, but we'd ultimately like to move in the Geoverse space to inclusive participatory roles, data vocabularies, digital twins is called out for IR standards. So this isn't the metaverse, right? This is, I think this is bigger, you know, simultaneously bigger and different than the metaverse. But it's important to understand that this is kind of like an actual grounding that was arrived on an open consensus. You know, some of the participants have disagreements, but, you know, everything does. And the other thrust that we have, you know, to consider in our motivations is what is open science? And, you know, here we have some, you know, NASA's been working and sort of pioneering this in the earth sciences for a few years, where they define sort of a leveling framework almost, where we look at, you know, what does it mean to be a fully closed system? And, you know, what are we moving toward into a fully open system? And sort of how do we gauge our progress here? So in a fully open system, these are the ideals. So teaching culture, you know, reproducible and fully transparent processes, and this is really key. Linked data and publications, everything's fully documented, so full provenance, you know, in all the ways that we mean when we say provenance, and free unlimited data access. So, you know, we're mostly over here, I would think, but, you know, from what I've seen, and we're moving this way. And so now we actually have this sort of path. Where are we moving to? And sort of like a little bit at a lower resolution, you know, a little higher resolution, you know, in terms of our actual agencies and large facilities, you know, we have these agencies and we can sort of define, you know, their spaces and their interfaces. And what do we want to do? We want to move toward this open ecosystem of trusted open ecosystems. And trust is a key concept here. We want to provide this knowledge network. And this gives us more coverage and use cases, holistic viewpoints, so, you know, outcome, use-driven discovery, and you know, that wisdom viewpoint. It allows facilities to specialize and then share capabilities and track knowledge application and decisions and outcomes. And I'm not going to go through all this text, but what I wanted to highlight here is, you know, we can take these ideas and then map them very specifically to personas, so we can actually validate, you know, we can go out in the community and validate, you know, what we're saying. So what we want to do is enable all these different users of this ecosystem to use the ecosystem and also contribute back to the ecosystem. And you know, we don't have this sort of capability now, is kind of the point, right? There's something missing from the existing models paradigm and the existing stovepipes paradigm. And we can outline this in a way where, you know, we're creating success for invalidatable ways for a lot of people. And that also means success in the workforce. So, you know, internally at large facilities and enterprises like NOAA, NESDIS, NCEI, we have all these defined roles and we have all this friction. And it's primarily due to some reasons, but, you know, we can say that, you know, the way we want to move to should enable all these different users to essentially make their jobs easier, make their jobs better, and ultimately to serve these kind of users, you know, in very specific ways. In terms of the enterprise, what does this mean? And I wanted to I added this slide, you know, the Center of Excellence model, but what we're trying to do for the enterprise is move to a sustained model, so a one NOAA model. And we're approaching this using some concepts that I think were really well expressed by Rich Hickey around 2011 in this talk called Simple Made Easy. And this doesn't get into knowledge graphs or any of that, which, I'd say Rich did with, spec, Clojure spec, and kind of attempted this and ran into a lot of issues, later in the late 2010s. But essentially what we want to do is follow this approach, right? We want to define simple as decomplexedness, and we want to separate that from the idea of easiness, which means, it's near to me, like it's near to users. So we want our system to be very simple and decomplexed as much as possible. We ultimately want to support so many users, and what that means essentially is we need a lot of concurrency, and we need a sustainable model. And we also need a lot of concurrency in literally everything that we do, contributions, uses, et cetera, et cetera. But we also want to build this in a way where we can expose it via really easy to understand tools and interfaces. So it means sort of a layered architecture approach. It also gives us full provenance of the computational enterprise. We want to approach this in a way where we have full provenance and, what are our data flows? What are the agents of our system? What is our network topology? What is our enterprise topology? Instead of having to go and ask someone, what we would like to do is just be able to query a system in plain text, in conversation or in some other near to me user interface. We also want to provide self-documenting processes to track evolution. This is really important in terms of our requirements. So it's not just making it near to users and supporting, sustainability, but we also, are balancing that with these idea of, NARA requirements, which is, the National Archival Records Administration, and this PARR directives, which is public access to research results. And, we have directives and to get to that open science sort of paradigm. And we've defined those actually in terms of PAR to align really well with that. So now we have to actually do that in our systems. So, also what we get out of this is, instead of now sharing technology and sort of like infrastructure technology, we're now moving toward a place where we have a shared reference model. And I think that's really powerful because, the shared reference model is something that you can hold in your head. You don't actually need a specific infrastructure, et cetera. Having folks move and share this idea of a reference model means we're turning like infrastructure problems into social problems. And this provides us the ability to eliminate stovepipes, do iterative improvements to systems. So, integrate it very, very surface level and then move deeper. And, it allows this self-sustaining model to grow, where we share resources of, well-defined types. We optimize to use cases. We can share libraries. And it allows us also to use the advanced tools in the next gen toolbox, which we'll get into. And it also allows this concept of federated interoperability, right? Because at an organization level, we can probably get to here. It'll be tough, but we can probably get to here. Now, if every organization is doing this, right, we're just going to end up with more than one reference model. It's just the reality. We're never going to get everybody to agree to a reference model. But if we're limiting these reference models and we have space complete reference models that can just self-describe and describe each other, the problem actually becomes very tractable of federated interoperability. So how do we get into this? And we'll jump in a little bit. So here's a quote from Phil Yang, who is the director and founder of the Spatio-Temporal Innovation Center, who I'm working with, for a few years now. And he came out with this really great, simple quote, I think, that says, "Architecture of a digital system defines flexibility, capability, and functionality." And I think this just sums up everything about, what a good architecture needs to do. And we kind of took that idea and said, this actually just means interoperability. So, how can we maximize interoperability? Because by maximizing interoperability, we can maximize flexibility, capability, and functionality. So, a communications problem defines essentially, by the software engineering body of knowledge, Conway's law, this interpretation of Conway's law, which says, anything we build constrains the things that are built upon it, right? So in architecture for something like this, for a facilities transformation, what we build in terms of enterprise service, to affect all these things that we want are ultimately, the constraint that people who build in our tools will have. So any properties and characteristics are carry through. So we need to be really, really careful and really cognizant of this, during all this, design phase. And here I'm tying in kind of this digital twin federation interop architecture. The concept of digital twins is becoming more and more important. We're doing a lot with digital twins at NASA and at NOAA, and with partners at CNES and the digital twins of the ocean. And IEEE is involved. At NSF, there's a lot of efforts. So there's a lot of efforts in this space. This is really, really coupled, movement here to sort of this transformation. And as we're building sort of these ideas of federated digital twin infrastructure, we need to agree that knowledge sharing is a federated problem. We need to consider inter-twin interoperability, and then inter-twin interoperability. And this kind of just recaps some of the earlier stuff I said. So diving a little bit deeper about what we're doing, right? So, we took all these inputs and we built this specification. An interoperability defined specification based on sort of the ideals of open science. And we applied model-based systems engineering, to build this thing out. So we developed a specification and we classified, satisfaction of all our requirements in terms of these interoperability sort of steps. And this is kind of a simplified view, right, of what we did: syntactics, schematics, semantics, legal interoperability. We've broken these things out. We've applied functional requirements, within these things to create this digital framework. Now we have, well-defined interfaces, so we can put an API on top of that. And the things that then people build with that framework become this digital twin earth. And because we have all this semantics in it, we're defining, knowledge and shared structure. And ultimately, we're getting this condition where we're capturing wisdom. And the real goal here is to capture that wisdom in the system itself, so we can then assess wisdom, and wisdom can sort of improve over time, which is really exciting. I just want to get into, so as we're leveraging this modern toolbox, we have these two approaches that sound like they map here to some of the things that we want to do. We have, this idea of meshes and fabrics. And sort of this is, like everything in informatics these days is really kind of fuzzy. But, what we want to say is that, there's a distinction here because we want to say there's a distinction in capabilities. And we need to use both of these things and capabilities of both to sort of achieve this goal, because we have some existing state and we need to progress through some step change. And so we need this concept of fabrics, right? We need centralized governance, focused communities, focused access patterns, but we want to actually put those into a broader context now inside this mesh, right? We want to enable sort of that step change and that future. So we're putting this community of fabrics, this ecosystem of fabrics into a larger mesh. And so that enables sort of this, community evolutionary governance, and sort of full provenance and that sort of thing. Some of the other tools in our toolbox that we see, these emerging motifs, and some of the efforts that I've been involved in, and sort of I've tried to divide, put these in sort of logical order from left to right. Here on the left, we see this, some things that are being developed at the US side in terms of Earth system digital twins. So in Earth system digital twins, we essentially have these really fast standalone, domain-specific processing units. They're integrated across some domains, but they're still sort of localized in the larger graph. And we have this idea of, these are brains, right? And all these brains can do really, really fast computations with digital records, digital replicas internally, but they can also communicate via, these unified interface subsystems, like a single interface to a single digital twin that's standardized. And now we can create constellations of these in sort of this, in sort of these digital factories. And sort of the European digital twins of the ocean ecosystem what I've seen is, and the architecture that they're working on is similar, but here the really cool thing is this unified collaborative environment, I think, where we have this concept of factories and people can share factories. And these all sort of talk to this digital backbone of big data scientific models. And towards the right, we have another NSF effort that I'm part of right now and that's ongoing, which is all these different products of like sort of if we're running models and stuff in here and we're producing like knowledge networks, here in the OKN we're combining these knowledge networks in a unified interface layer, and now we're putting an education ecosystem. So you can sort of see education ecosystem, and it's not one-to-one, but you can kind of see as we dig in, sort of zooms in, right? And we want to kind of use all these sort of tools as we do this. So diving in a little bit further, right, into what we're doing specifically at NOAA. So we have all these requirements. We have this idea of model-based systems engineering, this interoperability framing, and we want to support, basically this iterative enterprise transition, and then also support standards, to work with others. So what we did is, split everything out into these three, categories. We need technology, we need to choose tech, we need to choose a framework, and we need to choose a core data model. And we separate these things out, and then we convolve them together, and we ultimately end up with, this service, right? And we're defining it as a service because it's meant to be used as a service. It's really a service over a framework. And in terms of technology, we focused on the open standards of the semantic web, which is extremely scalable now in the ways that we'll describe. This covers ontologies, knowledge graphs, and data storage. We convolve that with this, this idea of a framework. A framework is a set of tools. It's a toolbox. It's a set of interfaces to tools. It's an abstraction. And we've chosen this idea of process as this fundamental dimension. And we've also sort of said, there are patterns of things. And sort of you can think of that in relational database land, like your tables, or NoSQL land, like your schemas. And so that's the patterns. And then every pattern, which is unvalued, corresponds to one or more templates, which are partially valued. And then, one template corresponds to many records. So we have this sort of hierarchy, and all of these things are sort of data captured in different spaces. And then we picked our core data model, which is, sort of been chosen. And this is an open standard. It's an old standard, but it's extremely good standard for this type of work, it turns out. And because it naturally, leverages this process configuration and provides this generic reference model for describing information. And the language of the OAIS, which is the Open Archival Information System, are SIPs, AIUs, AICs, and DIPs. These are all flavors of information packages. So all fit really well into building out an RDF, ontology, because you have information packages, you have then flavors of those, and you have flavors and that sort of thing. And then you can use these generic building blocks to create user-defined patterns. So like for an AIU, I might take and say, I need to create a pattern for a satellite granular. So I would take this concept of AIU, which is an archival information unit. It's an identity, it's an entity, and I would create a user pattern, in terms of structure and labels, but that thing would still be an AIU. So I have that sort of shared model, but I'm also letting users sort of use an API to configure everything that they want. Right? Here's a topology of sort of the system constructs. So, in our system, we have this idea of a process, right? And a process is composed of these classified tasks. And in terms of standards, this maps really well to the Open Geospatial Consortium's idea of processes. So a process with sub-processes. It's just a little bit, more general, I think. So we come up with this idea of a container that we can put everything and sort of make everything sane organizationally, and we can put interfaces on, we can run it, we can share processes, we can do all these awesome things with process, and we also conform to different, many different standards. specifications. So we have a lot of interoperability. And then every one of these tasks, right? So a process is composed of tasks in an acyclic digraph. So we have, a SIP task flows into an AIU task, or more than one. An AIU task flows into one or more AICs. AICs can flow into other AICs or DIPs, and DIPs are terminal. And so we have, define all this stuff in terms, every task in terms of a storage pattern that we want to, populate at runtime, which will become a record. And then we also tie that to some user code that's going to populate that. And this is open-ended. And we actually don't require message adapters at the code level for this. We just say, take in a JSON object and pass out a JSON object or an array of JSON objects. And then we'll let the system, do key-to-key mapping. So every one of these tasks is composed of these two units. This, again, is a user defined, so it could be an API call, some container, some other thing. This is tied to this computational execution environment. These things are all composed into a process template. And then the process template ultimately turns into a record at runtime. So, I define a template through my API. I've defined all these resources. Everything is declarative. I provide some runtime information. I create a record of that. And now I have like all these hierarchically organized, dynamically generated, super performant, super standardized records. And we've also split out now actually what the user wanted to produce in terms of SIPs, AIUs, ASCs, and DIPs. And we're also producing simultaneously that performance information in a separate dimension. So again, the idea of simplicity, right, in the decomplected sense. So there's a lot going on here, but ultimately what we've done is separate out everything into composable interfaces that only do one thing. Here's the big ConOps, and mindful of time, we won't spend too long on this. We can come back to it for the Q&A, which I kind of want to leave a lot of time for. But here you can see in the middle, we have those processes, and these all run independently, right? So there are multiple of these. The process itself is just a document. It's just a data document. It's actually an RDF document. And we're storing those as JSON LD, separable documents in this metadata bucket. Users can go in and create resources for these. So they define their own processes. They, different types of resources or users do and provide different things. So science and developers have a part in the system. Data managers have a part in the system. Everybody sort of has a role and a way to interact with the system, contributing user business logic, those task plugins, making process requests. And we can tie this into, basically any system, any system that we want, because our DIP model allows us to do that. Our submission model does, and the standards we use, right? We're just communicating over JSON via standard REST APIs and libraries. And every time we run this process or some well-defined process, we're creating a record. We're creating records for each one of these tasks. We're leveraging linked data to sort of hold all these things together. And so here's another sort of view that sort of puts some technology into it. We make process requests. We do some task transformations. We have actually buckets that we're storing these records in. We have something else that we're using called Amazon Neptune, which is a triple store, which we're using as sort of our hot storage, our digital replica. So it's more like, ephemeral data. So, this all sounds good. I think this is, people understand this and it's pretty well reasoned. And then, the question ultimately turns to, how do we do this, at enterprise scale? And that's actually the big question, for a lot of people that have killed a lot of these efforts in the past, right? And the thing that we came up with, and we sort of followed the digital twin standard of the industry, and we followed along with some of the work that's been done at NCEI in this space in terms of rejuvenation of various different old science systems over the years. And we've defined in terms of like research to operations to research, standard operating procedures. But we came up with this idea of a leveling framework. And we made sure our system supports this leveling framework. And each one of these levels we defined in terms of how much are you integrated with the process framing, right? How much have you integrated your systems? So at level 0, we have no integration, right? Your system is connected to the cloud in some way. At level 1, we have this baseline integration, and we call this a full integration, right? This is what we want people to get to say, okay, you're successful. You've managed to get your stuff in the system. And at this point, they've defined interaction with their system in sort of this process framing. So we're providing this metadata layer, this orchestration workflow sort of management layer, and they've connected their system. And now they're actually feeding all the interactions with their system at this level 1 integration. And as you climb these levels, you see more and more decomposition of their systems, right? And ultimately what we're getting to is a place where we're moving sort of simultaneously up this 5-star linked open data towards where everything is sort of linked and open data. And, this is sort of the framing that we're putting out there to sort of define our education ecosystem. A little more technical in terms of technology, but you can see this provides, I think, a really good view of how, these different workflows like AIUs, AICs, DIPs actually, work in the system computationally. So I have this big process document, which has task documents, which are just instruction sets. These things are fed in as messages, right? Or maybe we drop a file and have to look up the process definition. But ultimately, we're just bouncing it off an event bus. And we're looking up, these well-defined stereotyped workflows on the computational layer, which are doing all these stereotyped tasks like reading the instructions. And then these dark gray boxes are where the user code is run, right? So it takes a JSON object that's been well-defined. These are the keys we expect. These are the keys we expect to get out. Maybe we have an array of these things and we want to do some parallelization inside the workflow, which is fine, right? But the only thing that the user is responsible for is this. But you can see sort of then, every one of these things is just, we only have like 4 of these workflows. We actually have 8 to support a couple different modes of the computational infrastructure, but it's completely decoupled. But so everybody's code is just flowing through this, right? So it's extremely concurrent, and we're relying on the extreme concurrency provided by modern workflow management systems, which is there. I mean, it's there and it's very cheap. So you can see like somebody's process goes through here, and now they're, at the end, we're building the next task, and let's say it's an AIC task and a DIP task, and we run those in parallel, and then we do that again, and everybody's stuff is flowing through these, and then we let AWS scale up and scale down. It's completely serverless. It's really nice. We're kind of sort of wrapping up with time, so not to get too much into this, but here's sort of a different look about how are we supporting sort of rich semantic graphs here, and basically we just follow the OAIS, and we encode that in RDF, and we have this idea of member descriptions and collections, and we can populate multiple member descriptions for a given collection during runtime. And we're just mapping like what the user business logic runs. So it runs some set of keys, takes the values, does its processing, spits out a set of keys. We hold some map of key-to-key matching. And so now the user is just pumping out a JSON map, but we're actually putting those in context of these rich graphs. And here up on the right is demonstrating sort of, one of the graphs that we're populating, which is a Morton food web. But, to do this, it's complicated, to do it once. But in our system, right, we just define it in terms of a graph, and then we add it to a task, and then we're just passing out a set of JSON keys. So we're building a Morton food web every time we run it. Getting more into, the actual RDF and data model. Here you can see, our fundamental model, the information object. It holds data, and very importantly, it holds data as just bits. We've overloaded this with the idea of a field, right? So a field has a value. It has, multiple labels. It has, whether it's required, and it has a class and a namespace pair. And these things are coupled. And they actually overlay with the OAIS concepts of structure and semantic representation. So when users go in and specify these in the API, right, they can do that in the API sort of very easily. And then on the back end, we're actually just mapping to these structures. So now we have a standardized way of searching, which is like super critical. We want to be able to search across the whole space. And here you can see sort of the things that we can define and we would expect to define. And these are just suggestions, right? This is a mesh, so users are expected to go in and like form governance around different types of these things. And that governance can evolve over time, and we do automated provenance and tracking. Let's jump through these pretty quickly here. I'm just showing how the pattern space connects to the template space, connects to the record space. And as we're producing these things, we have links back to the template, links back to the pattern, so we can search these things really well. And when we put data into our system, we're actually validating against shackles, which actually define a valid pattern for an AIU, an AIC, and a DIP or a SIP. Here are some of the things that we're starting to do or envision doing in the past couple of years with the system. So here you can see sort of we're defining a process to extract some information from existing databases, do some normalization, do some further extraction, do some difference analysis, and then deliver that somewhere. And now all of this is encoded. And sort of we're encoding everything. So now we can, even look to sort of, swapping out some of the things that are done here or, trying new things. And that becomes very easy. Here's another effort, sort of a very AWS-y Amazon Web Service diagram. But this shows, another effort where we have a wildland fire storefront that provides lots of different standardized stuff. But ultimately, we're just running these processes. And so we're capturing all this in this knowledge graph. So right now we're seeding the mesh. We're developing and delivering educational materials. We're identifying beneficial partnerships, integration pathways. We're using advanced AI ML, like RAG techniques, to just demonstrate, conversational interfaces, which, we've showed off some demos so far. Pretty simple to get there. And we're building out, ultimately our first task for this is to build out this marketplace so people can share processes, tasks, parts of tasks, and just look at sort of that sort of stuff. And let's stop there. And hopefully there are some questions, and if not, that's quite a bit more.
Yeah, thank you, Ryan. No, this is great.